Welcome to the video lecture for section 7.1. This is for statistics 2023. And so the key concept here we're going to talk about in this lecture, we're going to talk about a point estimate, confidence interval, and also we're going to talk about sample size. So a point estimate is simply a single value used to estimate a population parameter. The sample proportion p hat is the best point estimate of the population proportion p. Now the point estimate is what we call an unbiased estimator. It's an unbiased estimator because the statistic p hat targets the population proportion p and is the most consistent of the estimators that could be used. Now here's an example. Gallup poll was taken in which 1,487 adults were surveyed, and 43% of them said that they have a Facebook page. Based on that result, find the best point estimate of the proportion for all adults who have a Facebook page. Because the sample proportion is the best point estimate of the population proportion, we conclude that the best point estimate of p is in fact 0.43. Now, if you're using the sample results to estimate the percentage, then the best point estimate would be 43%. Confidence interval. Confidence interval or interval estimate is a range, an interval of values used to estimate the true value of the population parameter. It's sometimes abbreviated as CI. Confidence level is the probability of 1 minus alpha, such as 0.95 or 95% of the confidence interval actually does contain the population parameter. Now the assumption is that the estimation process is repeated a large number of times. This is the central limit theorem. We did this in class a couple of weeks ago. Confidence level is also called the degree of confidence or the confidence coefficient. Now, what's the relationship between confidence level and alpha? When we get to hypothesis testing, alpha will become clear to you guys, but the following table shows the relationship between the confidence level and the corresponding value of alpha. When we start doing hypothesis testing, if we use an alpha of 0.1, then we have to create a 90% confidence interval. Always has to add either to 1 or 100%. If you use an alpha of 5% or 0.05, then you use a 0.95 or 95% confidence level and so on. Now, you got to be careful to interpret confidence intervals correctly. There's a correct interpretation and many different creative incorrect interpretations of the confidence interval. For the example here, we got 0.405 is less than p, less than 0.455. We had 95% confidence that the interval from 0.405 to 0.455 actually does contain the true value of the population proportion p. Now, an incorrect way of saying it is that there's a 95% chance that the true value of p will fall between 0.405 and 0.455. It is not a probability. Another incorrect way, 95% of sample proportions will fall between 0.405 and 0.455. Now, confidence level 95% tells us that the process we're using should, in the long run, result in a confidence interval limits that contain the true population proportion 95% of the time. And we showed this when we did all those samples, that some samples can be high, some samples can be low. Now here we have 20 different samples, and one of them does not contain, in this example, the population parameter of 0.5. But you can see that 0.5 is this horizontal line here, and all these vertical lines are the confidence intervals for different samples that were taken. And you can see that the green one does not contain the actual population parameter. So when we do a confidence interval, this is in fact what we're saying. Now, next thing is critical value. Critical value is a number on the borderline separating sample statistics that are significantly high or low from those that are not significant. Now, the number z alpha divided by 2 is a critical value that is a z-score with the property that is at the border that separates an area of alpha divided by 2 in the right tail from the standard normal distribution. And so here's your bell curve, normal standard distribution. And so these lines here on the left and on the right are the areas that are alpha divided by 2. Now we're going to find a critical value, z alpha divided by 2, that corresponds to a 95% confidence level. 95% confidence level corresponds to an alpha of 0.05, so alpha divided by 2 is 0.025. Now the figure in the next slide will show the area in each of the green shaded tails is in fact 0.025. Now we find that z of alpha divided by 2 is equal to 1.96, and by noting that the cumulative area to its left must be 1 minus 0.025 or 0.975. Now we can use technology to find that the area that corresponds, the value that corresponds to the left of the area of 0.975 corresponds to a z-score, or z value of 1.96. So for a 95% confidence level, the critical value is therefore Z alpha divided by 2, which is 1.96. Now, when finding the critical z-score for a 95% confidence interval, we use a cumulative left area of 0.975, not 0.95. So think of it this way. Our confidence level is 95%, our alpha is 5%. So we divide the alpha by 2, we get 0.025. So the cumulative area from the left, excluding the right tail, has to be 0.975. So over here on the right, you see how you have a plus or minus 196, so we got the positive 1.96. And so everything to the left of that line is cumulative area of 0.975. When you're doing a two-tail, you take your alpha and you half divided by 2. Remember, the area underneath the curve is 100% or equal to 1. So the previous example showed that a 95% confidence level results in a critical value of 1.96. Now, some of the most common critical values are here. 90% or 10% alpha is 1.645. A 5% alpha, a 95% confidence level is 1.96. An alpha of 0.01 has a confidence level of 99% and a critical value of 2.575. Now, next thing we're going to talk about is margin of error. When data from a simple random sample are used to estimate a population proportion P, the difference between the sample proportion P hat and the population proportion P is an error. The maximum likely amount of that error is called the margin of error and is denoted by a capital E. So there is a probability of 1 minus alpha, such as 95%, that the difference between P hat and P is E, the margin of error, or less. So the margin of error E is also called the maximum error of the estimate and can be found by multiplying the critical value and the estimated standard deviation of the sample proportions. Here's the formula which we use in class. So E, margin of error, is equal to your critical value times the square root of P hat times Q hat divided by N, where N is your sample size. Now we're going to construct a confidence interval used to estimate a population proportion P. Some of the things that we talked about in class: P is equal population proportion, P hat is sample proportion, N is the number of sample values, E is the margin of error, and then your critical value. So some of the requirements: has to be a simple random sample. Conditions for a binomial distribution are satisfied. There's a fixed number of trials. The trials are independent. There are two categories, right? Either for both of these. So those two categories will be successes or failures. So the formula is P hat plus or minus E. And of course, using the entire formula, it will be P hat plus or minus the critical value times the square root P hat Q hat over N. Now, we round confidence interval limits for P to three significant digits. Usually I do 2. And so what's the procedure for constructing a confidence interval for P? Verify the requirements in the preceding slides are satisfied. We're going to use technology or a table to find a critical value. And then we're going to evaluate the margin of error. We're going to be using the value of the calculated margin of error and the P value and the value of the sample portion P hat. We're going to find the values of the confidence interval limits P hat minus E and P hat plus E. And I'm going to substitute those values in the general format for a confidence interval. So we noted that a Gallup poll of 1,487 adults showed that 43% of the respondents have Facebook pages. So our sample size is 1,487, or P hat is 0.43. We're going to find a margin of error E that corresponds to a 95% confidence interval. We're going to find a 95% confidence interval, and then based on the results, we can safely conclude that fewer than 50%. Based on the results, can we safely conclude that fewer than 50% of adults have a Facebook page? Assuming that you're a newspaper reporter, write a brief statement that accurately describes the results and includes all the relevant information. So the first thing, polling methods used by Gallup organizations for some samples that are considered to be random samples. Conditions for binomial experiments are satisfied. With 43% of the respondents having Facebook pages, the number of Facebook pages is 639. If 639 of the 1,487 subjects have Facebook pages, the other 848 do not. So the number of successes is 639. Number of failures is 848. Both are at least 5. So here's the manual calculation. The margin of error is found by using the formula. So E is equal to your critical value, which in this case is 1.96. times the square root of P hat, which is 0.43, times Q hat, which is 0.57. Remember, P hat and Q hat have to equal to 1, divided by the sample size, which is 1,487, and that gives you 0.0251636. So constructing a confidence interval is really easy now that we know that p hat is 0.43, margin of error is 0.025. We're going to simply substitute these values to get the result. And of course, we end up with 0.405 less than p less than 0.455. Based on the confidence interval obtained in Part B, it does appear that fewer than 50% of adults have a Facebook page because the interval of values, 0.405 to 0.455, is an interval that is completely below 0.5. So the summary. Here's one statement that summarizes the results. 43% of adults have Facebook pages. The percentage is based on the Gallup poll of 1,487 randomly selected adults in the United States. In theory, in 95% of such polls, the percentage should differ by no more than 2.5 percentage points in either direction from the percentage that would be found by interviewing all adults. Analyzing polls. When analyzing polls, consider the following. The sample should be a simple random sample, not an inappropriate sample. Confidence level should be provided. Sample size should be provided. And except for relatively rare cases, the quality of the poll results depend on the sampling method and the size of the sample, but not the size of the population. Never think that polls are unreliable if the sample size is a small percentage of the population size. Again, the population size is usually not a factor determining the reliability of a poll. Now, finding the point estimate and E from a confidence interval. Point estimate of P hat is equal to the upper confidence interval limit plus the lower confidence interval limit divided by 2. The margin of error is the upper confidence interval limit minus the lower confidence interval limit divided by 2. So, this article, High Dose Nicotine Patch Therapy, includes this statement. Of the 71 subjects, 70% were abstinent from smoking at 8 weeks. 95% confidence interval, 58% to 81%. Use a statement to find a point estimate p hat and the margin of error. So we get a 95% confidence interval of 0.58 to 0.81. The point estimate p hat is the value midway between the upper and lower confidence limits. So we get that the p hat is equal to 0.695. Now the margin of error can be found by simply subtracting the upper limit from the lower limit, so we get 0.115. Now the next thing is finding the sample size required to estimate a population proportion. Again, some of the notations, p hat, and e, and the critical value. So the sample must be a random sample of independent sample units. When an estimate p hat is known, we use the formula n is equal to the critical value squared times p hat times q hat divided by the margin of error squared. When we don't know p hat, to estimate the sample size, we use the critical value squared times 0.25 divided by the margin of error squared. Now, if the computer sample size n is not a whole number, we round the value of n up to the next larger whole number. So the sample size is sufficient instead of being slightly insufficient. For example, we round 1067.11 to 1068. Now, what percent of adults make online purchases? When the author was conducting research for this chapter, he could find no information about the percentage of adults who make online purchases. Yet that information is extremely important to online stores as well as the brick and mortar stores. If the author were to conduct his own survey, how many adults must be surveyed in order to be 95% confident that the sample percentage is in an error by no more than 3 percentage points? So we're going to make the assumption that the recent polls showed that 80% of adults make online purchases. Assume that we have no prior information suggesting a possible value for the population proportion. With a 95% confidence level, we have alpha of 0.05, critical value is 1.96, margin of error is 0.03. The prior survey suggests that p hat is 0.8, so q hat is 0.2. So, because we have an estimated value of p hat, we use the first formula. And again, we must obtain a simple random sample that includes at least 683 adults. For Part B, we have no prior knowledge of what the population proportion is or the sample size. So we use the formula, which is the critical value squared times 0.25 divided by the margin of error squared. We use that formula, we get 1068. So we must obtain a simple random sample that includes at least 1068 adults. So, to be confident that our sample percentage is within 3 percentage points of the true percentage for all adults, we should obtain a simple random sample of 1068 adults, assuming no prior knowledge. By comparing this result to the sample size of 683 found in Part A, we can see that if we have no knowledge of a prior study, a larger sample is required to achieve the same results when the value of p hat can be estimated. That's the end of 7.1. Thank you.